Okay, so welcome back everyone to my penultimate lecture. So the last two lectures will both be about aspects of the local structure of minimum spanning trees. So we'll sort of set up the local limit framework and then use a result of Aldous and Steele to derive the expected weight incident to a vertex in the minimum spanning tree. And then we'll also use sort of investigate the local structure of the local limit, and in particular see that locally the minimum spanning tree looks like a one-ended infinite tree. So let me remind you of the result we've already seen in the local limit framework a little bit informally. So this is from the first week of the course. So we saw that for a uniformly random tree, so there's no optimization here, just random labeled tree. So then the local structure near the root so maybe I should add the word asymptotic here. I'll always be thinking about asymptotics as the tree becomes large. And so the asymptotic local structure near the root looks like a sort of single infinite path off of which are attached independent critical Poisson bien-aimé trees. So these are IID. And I remember I used this notation for a bien-aimé tree with offspring distribution Poisson 1. Okay. And so now we'd like to ask and answer the question is, what's the local structure of the MST of Kn with IID uniform weights. Okay, so let me actually start using Tn to denote this tree instead of the uniform tree that it was before, and my weights are as usual UE. Okay, and now we'd like to think of the weights on the edges as lengths. Okay, but if we do that, we sort of have a problem. Anyone who looked at the exercises that has been looking at the exercises that I said, and in particular an exercise from Kavita's week, said that, if we look at the graph, Gn C log n over n for large C, this then with high probability that graph's connected. So this was an exercise. This is in fact true for any constant C greater than 1, but the exercise was to see that this graph is connected for large C. Okay, so if you think of this graph as of the edge weights as lengths, that's saying that every vertex in the graph will have at least one neighbor at distance order log n over n. So in particular, little o of 1. So if you sort of think of those, if you now think about the graph becoming large, that's saying that lots of vertices would be sort of collapsing in on themselves and becoming sort of infinitely close in the limit. So if we want to see something non-trivial, we need to scale up the edge weights. Okay, so we'll do that so that the typical sort of minimal edge lengths have order 1 rather than order 1 over n. So we scale up the lengths by multiplying by n. Okay, and then we can hope to see a sort of non-trivial asymptotic local structure. Okay, so we'll fix some vertex whose local structure we want to examine, and write list the local edge weights now in increasing order. Okay, so these are the edge weights incident to V in increasing order. And then I'll use P to denote their scaled version, because they're going to, after scaling, look like a Poisson process. Okay, so P1 up to Pn minus 1 is just n U1 up to n Un minus 1. Okay, and so then I claim that for any, so that this sequence after this scaling looks like a Poisson process, in the sense that for any fixed k, if you look at the first k terms, then that converges in distribution to the first k atoms of a Poisson process on the non-negative real line. So the first k points in a rate 1 Poisson point process on 0 infinity. Okay. So to prove this, you should sort of check that the joint distribution of this converges to the joint distribution of that. I won't do that in full detail, but let me just say that quickly do a calculation which tells you sort of why this is true. So if we just look at the cardinality of the number of integers I, such that the point, the ith point is at most some real number x. So this works for any x positive, right? That's just so this set has size, at least 10 if 10 of these original points up here were at most x over n, because we scaled up by n, right? So this is precisely distributed as a binomial with n minus 1 trials and success parameter x over n. That's the probability an individual one of these contributes to this set. Okay, and that converges in distribution by the Poisson approximation to the binomial to a Poisson with parameter x. Okay, so I mean that's sort of the fundamental reason why this claim is true. Okay, so that means that if you look at if you look at this vertex V, and you look at its closest neighbor and second closest neighbor and third closest neighbor and fourth closest neighbor and so on, right? Then these edge lengths look like the successive points of a Poisson point process on 0 infinity, getting longer and longer. Okay, so I won't generally draw them with the sort of Euclidean length actually representing the length, but you should think of the lengths increasing as we go from left to right. Okay, but of course, so we know that these smallest edge weights are important for the minimum spanning tree. If we use Prim's algorithm started from V, the first thing that it'll do is add the smallest edge incident to V. Okay, but we need more information than is contained just in the sort of first step picture here, because the second thing Prim's algorithm wants to do is take the smallest weight edge that leaves either of these two vertices, and that might be a neighbor of this first child, right? So we need to know more about the local structure. We need to go out further if we want to explain the local structure, and so the picture we get, we need to expand this picture to also talk about the small weight edges leaving each of the neighbors of V, and so on. Okay, so this is the picture we get is really very much like the picture that Jean-Christophe had in his lecture today when he was explaining the Poisson-Dirichlet cascades. But in my setting, where my edge weights are a little bit different than his, he had some inhomogeneous Poisson process which he normalized, and I have a homogeneous Poisson process, and I'm not normalizing it. I'm letting the weights be unbounded. They don't sum to 1 like they did for him. Okay, but so the structure that I'll get out of this, I'll justify this in a second, but when we explore the local structure of the neighbors of a given vertex and then their neighbors, at each step we are again going to see something that looks like this a rate 1 Poisson process. Okay, the atoms of a rate one Poisson process. So the recursive structure we get is called the Poisson weighted infinite tree. Or PWIT for short. So this is the random weighting of the Ulam-Harris tree. Remember, this is the tree with vertices. So the union of n to the n, where n to the 0 is defined to be just the empty set. So a given vertex, v1 up to, a given string of length k, its children are just strings of length k minus 1 that you get by appending an integer on the end. So the weights, so the way we're going to assign the weights is, so weighting the children of each node according to an independent, so independent over different children, over different nodes. So rate one Poisson point process on 0 infinity. Okay, so the picture is, so here's the root labeled empty set. And then the edges from the root to its children have labels, P, I'll call them P empty set 1, P empty set 2, etc. Those children are 1, 2, 3. And then 2, we'll have another independent Poisson process here. So it's atoms in ranked order P2, 2, 1, P2, 2, 2, and so on. Okay, so this is 2, 1, 2, 2, etc. So my labeling is a little bit different from Jean-Christophe's, and it's also a little bit redundant, right? I don't, if I tell you that, I could just index by the child label and you would know that it was meant for the sort of weight of the parent edge, if you like. But I like, it's useful for me at least to refer to these as sort of living on the edges. So this 2, 2, 1 indicates that the weight sits on the edge from 2 to 2, 1, and so on. Okay, so this structure repeats recursively at the children of every node of the tree. Okay, so the if you like, the set of processes then are so P, V, VI. I at least one, where V is any node of the Ulam-Harris tree. So these are independent. Okay, and so the goal is, of this lecture and the next, I guess, is to describe the asymptotic local structure of Tn in terms of this Poisson weighted infinite tree, or really of its minimums, of the minimum spanning forest of that Poisson weighted infinite tree. So okay, and here I should say the wired minimum spanning forest. So this is a setting, well, I'll get to that, but this is a setting, when you talk about the minimum spanning forest of a tree, it's only interesting if you take the wired one. If you take the free one, then it's just the whole tree. If you take the wired one, then you can see interestingly non-trivial structure emerge. Okay, so so in order to explain why we should hope to describe the local structure of the minimum spanning tree of Kn in terms of this object, which, so far all I've done is some very vague heuristic saying that maybe locally the tree looks, if we think of the weights as lengths, then the local structure in the complete graph looks a bit like the local structure of this Poisson weighted infinite tree. And so, I'd like to justify that in a bit more detail, that the two local structures are similar, but also to explain the framework of local weak convergence in more detail, because it's quite an important and powerful framework, and it turns out to be particularly valuable specifically when studying minimum spanning trees, though not exclusively. So before I sort of further connect the PWIT with the complete graph, let me talk about local weak convergence. Okay, and just before I do that, I can't resist the bad joke. So I've heard two stories about this name from the two people who invented it. David Aldous told me that they named it the PWIT because it's a very PWITty object. And Mike Steele said they named it the PWIT on the theory that when you're naming an object, you can do two things. You can either give it a really good name and hope that it sticks, or give it a really bad name and hope that people change the name and name it after you. I don't know which story is true, but they might have had different motivations, the two authors anyway. Okay, so you can think of that name what you will. It seems to have stuck anyway. We're going to, talk a little, so set up the framework for local weak convergence in a bit more detail before we justify that this PWIT really is the local, the right limit notion for the randomly weighted complete graph. So we need to, there's sort of two steps to this, I could do it all in one step, but it'll be clearer, I think, if I start with unweighted graphs and then move to weighted graphs. Okay, so here there will be no proofs, but there will be some examples. If I'm given two rooted weighted graphs, okay, so all the graphs in this section will be rooted because we're interested in the local structure near a point. So the point will always be our sort of root vertex. Okay, so let's start with connected rooted graphs with all degrees finite. So I'm not insisting that they're finite graphs, but the degrees need to be finite. Okay. So a rooted isomorphism from G to G hat is a bijection between the vertex sets. So phi from V to V hat, which preserves edges and non-edges and also the root. So we should have phi of rho is rho hat, okay, and we want that for any pair of vertices of the domain. So for any UV and V, UV is an edge of G if and only if phi of U, phi of V is an edge of G hat. Okay. So if G and G prime are rooted isomorphic, then we denote that G is equivalent to G hat. Okay, and now the only thing this is saying is for our sense of convergence, we're really not going to be caring about labels. Okay, so we're only going to consider graphs up to rooted isomorphism. So it doesn't matter if the vertex set is 1 up to 26 or A up to Z, as long as the structure, the local structure is the same. So now to look at the local structure, let me write so GR for the subgraph of G, which is just where you only keep things that are at graph distance at most R from the root. Okay, so the subgraph of G, I should say the induced subgraph. So where we, the vertex set is so VR, which is all of the vertices that have distance at most r from the root, and then saying it's an induced subgraph means you keep all edges of E that connect vertices in VR. Okay, and now I can so with this notion I can define a distance. So I'll write dr for the distance between G and G hat. Now let's say that this is 1 over the largest R such that GR and GR hat are rooted isomorphic. Okay. So, you know, if, you know, here's one graph and here's, here's another graph, and the roots are here and here, right? Then I can. There's a rooted isomorphism that of the distance 2 neighborhoods of the roots, right? These two graphs are isomorphic. But if I go out to distance 3, they're no longer isomorphic. So then this supremum would be 2, and the distance between these two would be a half. Okay, the definition clear? So, you know, maybe I should say then R in N here. When we move to weighted graphs, I'll want to allow real distance, but here it can just be integer. Okay, and so now, you know, I'll leave it to you to check that this, whoops, there's no R there. So the exercise is that this satisfies the triangle inequality. Okay, it's not technically a metric, right? Because if I have 2 isomorphic graphs, they'll have distance 0 under this distance. But we're only going to care about graphs up to isomorphism. So so we'll just quotient out. So I'm not going to. There's a question in the chat whether the R on the left is short for rooted distance. I removed the R on the left actually. I'm just going to use D. But it could have stood for rooted, yeah, if I'd been faster on my feet. So, you know, we'll just quotient out by the isomorphism relation now. So, right, G, script G, for the set of isomorphism equivalence classes. Of rooted. So I'll use the phrase locally finite to mean that all the degrees are finite. So locally finite graphs. Okay. And so with that definition, then the pair G with this distance D forms a complete separable metric space. And, you know, so these are the sorts of spaces that we like to do probability on. You know, for those who haven't sort of necessarily seen much probability beyond Euclidean space, you know, like countable additivity is kind of a big part of the foundation of rigorous probability, right? It's right in the definition of sigma algebras. And so when you work in a space that, well, completeness, you know, is very natural for analysis, and separability means that there's a countable dense subset. It kind of allows for countable approximation of most of the things you want to understand. That kind of, these end up being kind of the key properties that allow you to extend a lot of probability theory, the things we normally like to have happen in probability theory, to spaces beyond beyond Euclidean spaces. Okay, so so in particular, you know, convergence and distribution is defined by convergence of expectations of bounded continuous functions and things like that. you know, one small comment here. So this D really, I mean, I'm abusing notation a little bit because here D was defined for graphs, and now I'm applying it to equivalence classes. But the point is that if two, you know, it doesn't matter if I want to measure the distance between two equivalence classes, it doesn't matter what representative I pick because the distance only cares about isomorphism anyway. Okay, so so this is the sort of space of random variables that we work in for studying unweighted local convergence. You know, so for a sequence Gn, I'll put the limit right in of so G-valued random variables. You know, we say that Gn converges in distribution to G infinity if the expected value of f of Gn converges to that of G infinity for all bounded continuous functions f from G to R. Okay, so that's the sort of standard definition of convergence and distribution in a complete separable metric space. I'm just making it explicit this once. Now, you know, having, you know, you have to think a little bit now about what continuity means in this setting, right? And continuity with respect to this metric, the metric we put on G, means that, you know, we only care, the error between two measurements in this space will be small if the two graphs agree out to some large distance up to isomorphism. So that says effectively that we can measure and capture local behavior, but not sort of global behavior about things infinitely far away. Okay, so you need to sort of think a bit about that for yourself. But now, you know, with this notion of convergence and distribution, if we go back to the case of a you know, a uniformly random tree, then the convergence that we sketched informally before really is now a rigorous convergence and distribution. Okay, that was mentioned at the start of the lecture. And then there are a couple others that, as someone pointed out in the chat, this construction also appeared in Kavita Ramanan's lectures, that were also alluded to in her lectures, which I'll remind you of or tell you if you didn't attend those lectures. So if we look at a uniform random 3 regular graph, with so vertex set n and a random root, then so Gn converges in distribution. So every vertex has degree 3, and the limit can be described just by a sort of local calculation, which, so this is, you know, one of your exercises for today, but it's to check this. That sort of with high probability, such a graph won't have any cycles sort of within any fixed bounded distance from a fixed point with high probability. And so that means that the local limit will really look like an infinite 3 regular tree. Okay. And then there's one other example. So that's sort of one of the most standard examples of local weak convergence. The last one I want to mention, Kavita also mentioned, but I'm going to do it a little bit differently from her. So she talked about the complete binary tree with n levels. And for her, the root was the root of the binary tree. So then the limit picture is just an infinite complete binary tree. Okay. But if you instead take a random root, right? Well, in a binary tree, there's twice as many vertices at each level. So the lion's share of the vertices are not close to the root of the tree, they're close to the leaves of the tree. Okay, and so if you think about what the convergence and distribution will be to, it'll be to the root that you see will be close to the leaves. So what you end up seeing is a structure which is called the Canopy Tree. So you sort of start from the leaves, and then going up from the leaves, you see a complete binary tree. So it's a complete binary tree sort of viewed from a leaf. except that it's not exactly, the random root won't exactly be a leaf, right? Because asymptotically, half of the vertices are leaves, and a quarter are at distance 1 from a leaf, and an eighth are at distance 2, and so on. So what you'll see is that is a root that sits at a geometric random distance from the leaves. Okay, so that's also in the exercises to sort of check that for yourself, but I think it's quite a pretty structure, and the sort of story is already fairly compelling, I think. It's not hard to believe that that's the correct local limit. Okay, so so much for unweighted graphs. Any questions about that? Because I'd like to move to weighted graphs now. This is all, I mean, both the slides are online and this is actually typed up in the notes, by the way. So if you're not keen on trying to scribble all this down while I lecture, you can look at those. You can look at those. Right. So now let's move to weighted graphs. So so now our basic objects are going to be still rooted, but also with weights. So for a weighted rooted graph, so that'll be VE row as before, and now we additionally have a weight vector, so weighting the edges of the graph. Okay, so for such a graph, remember I said that we're going to think of the edge weights as lengths, and so then we can use them to define a distance between vertices of the graph. So we'll define the distance between vertices u and v in this weighted graph G to just be the smallest weight of any path between u and v in the graph. So the weight of a path is just the sum of its edge weights, and so we take the infimum over paths from u to v in G. Okay, and now we'll say that G is locally finite if there are only a finite number of vertices at distance at most r from the root for any positive r. Okay, so we'll define VR to be the set of vertices such that the distance from rho to v is at most r. So this should be finite for any r, and then the graph is locally finite. Okay, so like before, I mean, so you can you can always interpret an unweighted graph as a weighted graph just by giving every edge length 1 or weight 1, right? Right, so this is sort of a generalization of the previous framework. Question in the chat, whether we assume edge weights are strictly positive. I think we probably will, yeah. Otherwise you're effectively doing a vertex identification and then talking about bijections between the vertex sets might get a little bit annoying. So let's assume all the edge weights are strictly positive. So all greater than 0, or at least almost surely positive, say. So now I'll write just like for unweighted graphs. So GR will be the sort of induced subgraph consisting only of vertices at distance and most r, right? So ER is the set of edges such that both endpoints are in VR, and then this vector is just the sort of the relevant subvector of the original weight vector. Okay, and so now, the definition of similarity is a little bit more involved for weighted graphs, and a simple example will explain why, right? If you imagine, say, let's think about just a very simple example of like a triangle where all the edges have weight 1 minus delta, right? Then you definitely, and I guess I need to designate one of the vertices as the root. So the root is rho down here, rho delta, right? So you would definitely want that as delta tends to 0, that that this graph converged to a triangle with all edges of length 1, right? But if we sort of try to if we pick some parameter between 1 minus delta and 1, then there won't actually be a rooted isomorphism between the graphs, the sort of the graphs GR over here and the limiting graph, right? Because if we're at 1 minus delta over 2, we've just reached these two vertices over here, but we haven't reached them here. So we need to give ourselves a little bit of wiggle room, both in the in the distances that we measure, in order to deal with that sort of issue. Okay, so let's say that G, so two now weighted rooted graphs are close. If we can find so two numbers x and y, which are at least r, and whose difference is at most 1 over r, and so that if so we're thinking of both x and y as kind of, well, x will be the distance we go out in G, and y will be the distance we go out in G hat. And then we should see similar graphs when we go at these distances. So we've given ourselves this little 1 over r wiggle room. So then we want there to be a rooted isomorphism. So phi from Vx Ex rho to V hat x E hat x rho hat. Okay, so the isomorphism has to exactly preserve the structure of the graph. Okay, and then it has to approximately also preserve the edge weights. So so it should satisfy that the weight of E minus the domain weight of E, well, let me, so I'll start again. The weight of UV minus W hat of phi U, phi V is less than 1 over R for every edge UV in EX. Right, so now we're, I really want hat V, thank you. That should be, these should be, someone pointed out those should be Y's over on the right. Okay, so we have we find these large parameters, so you think of these as being very close. If R is large, we can find isomorphisms between large unweighted neighborhoods, large neighborhoods of the roots of each of the graphs, which approximately preserve the edge weights. Okay. Don't comment in the chat. Don't you need to replace Vx by approximate balls? So the approximation being here, I'm not sure I understand the point. Okay, I'll postpone that chat. Okay, so so now let's say that so that gives us a notion of closeness. And if you look at locally finite graphs, then you can also talk about isomorphism. Well, I guess you can talk about that regardless. So we'll say that so G and G hat are isomorphic if we can find a graph isomorphism. So from V row to V hat E hat rho hat, which preserves edge weights. Okay, so now just like we did for unweighted graphs, the class that we study will be isomorphism equivalence classes, so I'll call it G star. This is a set of isomorphism equivalence classes of locally finite weighted rooted graphs. Okay, and then if I'm given two elements of this class, I'll define a distance between them to be just like before. So I'm really working with, you can think of this as these as being kind of representatives of the isomorphism equivalence classes. So 1 over the largest R such that G and G hat are R close. Okay. So this, so if these two have distance under this D star, which is at most 1 million, it means that you can go out distance greater than 1 million in both of them and find isomorphic neighborhoods whose edge weights all line up to within additive error of 1 over 1 million. Okay, so this again gives you a complete separable metric space. Okay, so for separability, you can think of only allowing rational weights, for example, and that's one way to see that kind of. If you look at finite isomorphism equivalent classes of finite graphs with rational edge weights, then that forms a dense, accountable dense set within this space. Okay, so now the key, with that setup, we can formalize the connection between the randomly weighted complete graph and the PWIT. So if we let Gn be Kn with these edge weights, so N UE, and say root 1, then so then Gn converges in distribution to the PWIT in the space G star D star. Okay, so I'll say that there's a question in the chat, MSTG and no. So I'm talking about just the complete graph. We'll get to the minimum spanning tree in a second. But for now, I'm just saying the local structure of the complete graph itself with these edge weights is given by the Poisson-weighted infinite tree. We haven't yet gotten to the minimum spanning tree structure on top of that yet. That'll come shortly. Okay, so I'll take a 3-minute break and get some water. I'll just look at the chat first. There's another question. To be clear, with this definition, an edge of length 2 isn't the same as the path of 2 edges each of length 1. That's correct. Yeah. So I require isomorphism, which preserves local structure, which preserves the graph structure and the edge lengths, not just the sort of I don't know, metric structure, ignoring the points continue to play a role. Yeah. I mean, certainly from the perspective of minimum spanning trees, there's quite a difference between an edge of length 2 and 2 edges of length 1, right? I mean, you might choose to take one of those 2 edges of length 1 and put it in the spanning tree, but not the other because the far endpoint had some cheaper route. So that there is from the perspective of the kind of optimization we want to do, there really is a difference between those 2 structures. Right. Good. Yeah, I'll just get some water. Okay. So I'd like to start talking about this fact. Right. And sort of the first, there's a variety of ways that one could prove this, or sort of structure the proof. I think there's just sort of one mental picture to have, but in terms of how to actually write it down, there's a variety of ways you could do that. But what I want to do is just think about kind of only looking at boundedly many neighbors of any given vertex. And so maybe it's worth saying as a sort of preliminary remark, that if so for any locally finite graph, G, if you look at any vertex of G, then it sort of only can have, it can only have boundedly many neighbors at bounded distance, because the graph is locally finite, right? So if if I look at the so if the edge is incident to V in increasing order of weight are, EI, I at least 1, then the weight of EI tends to infinity as I tends to infinity. I mean, or another possibility is that this vertex just only has finitely many neighbors. But if it only has finitely many neighbors, you can sort of think of this, the weight of EI as formally being equal to infinity after some point. But in this graph, for example, in the Poisson weighted infinite tree, right, each vertex has infinitely many children, but only only boundedly many of them have weight at most 100 or 1,000 or something. Okay, so this means that if I look at the millionth neighbor, it's going to be so far away that it can't make a big difference to this notion of local convergence, which only cares about bounded neighborhoods. Okay, so in order to prove a convergence in distribution in this space, I can think about only looking at some bounded number of neighbors of each vertex. As long as I can make that bound as large as I like and still the local structures agree asymptotically, then that's equivalent to local convergence. Okay, so so that is to say, to establish local convergence, it suffices to only consider boundedly many neighbors of each vertex. Okay, so to be a little bit more precise, for the PWIT, let's restrict our attention to I'll call it I'll give it a superscript k, so PWIT k, so this will be the subgraph with vertices, so the root and then the first k generations, but only looking at the first k neighbors in each generation. Okay, so that's, if k is 3, then we go, the first 3 children, and then each of their first 3 children, and then this would be our PWIT 3, right? And that's just, this comment is sort of saying that, looking out to a fixed distance and looking out to a fixed weight are the same as long as we can do arbitrarily large distances or weights. But it's a little bit nicer to have a deterministic number of children to consider rather than a random number. It's the only reason I want to do that. Okay, so what's the equivalent? So this is looking at a bounded number of nearest neighbors out to a bounded distance in the PWIT. And we could do the same thing in the randomly weighted complete graph up here, Gn. Okay, so we could take, so let's let so Gn superscript k. So this will be the subgraph of Gn that so has the so k smallest weight neighbors of each vertex out to distance k. Okay, so but now I really want to think about the smallest weight neighbors sort of in the unexplored portion of the graph. Okay, so I'm going to, so by that I mean, so starting from vertex 1, we'll look at the k smallest weight neighbors of vertex 1, and then for each of those vertices, we'll look at the k smallest weight neighbors out in whatever's left of the complete graph. Okay, and then for each of those, we'll look at the k smallest weight neighbors out in what's left and so on. So, so that's just because, if this is the, maybe I'll draw it vertically to agree with the drawing of the PWIT there. If this is the smallest weight neighbor of vertex 1, this is a very small weight edge. So there's good odds that the smallest weight edge leaving this vertex actually points back to vertex 1. But I'm interested in exploring sort of toward the unexplored part of the graph. So I'm going to take my k going outward. Okay, so let me be more precise. So so our graph GN naught, let's say, so let's take GN like K naught to be just the vertex 1. Okay, and then then for each I from 0 up to K minus 1, if I show you the graph GN KI, so this will be the first kind of I levels going out. I'm looking at K smallest neighbors each time. Then, so for each vertex V on the ith level, so in GN KI minus GN KI minus 1, we'll add the K new smallest or closest neighbors. So SV will be the set of the K nearest neighbors of V in what's left of the graph, so in n minus the vertices of GNKI. Okay, and then we'll let GNKI plus 1, that's adding the next layer, so that will have vertex set. So the vertices of GNKI plus all these new vertices. So we have to add these sets SV for each V in GNKI minus GNKI minus 1. So the current kth layer. Okay, so we start from the root, we add its K nearest neighbors, and then for each of these vertices we add its K nearest neighbors. And in theory, these sets could overlap, right? I mean, the K smallest weight edges leaving the nearest vertex to 1 toward the rest of the graph could head toward the same vertices as some of the K smallest edges leaving the third nearest neighbor to 1. So this is just some finite graph. These edges have random endpoints. Okay, but you know, the typical local structure is not that one sees overlap here. It's that these endpoints are all distinct vertices in what's left of the complete graph. Okay, because you know, if we think about let's think about the edge weights on. We're interested in showing that this picture GNK. Okay. Oh, I didn't finish, I guess. So then, so GNK is the graph with the K taking sort of K nearest neighbors out K steps to so each of K steps. So that's just GN of KK in this notation. Okay. So what we'd like to say is that this graph looks a lot like this PWIT K that we get by looking at the K smallest neighbors at each step out to distance K, right? Yes. So here, that's right. So here there's a comment in the chat. This is distance K in the graph metric, not the edge length metric, right? So you see that here. I'm really taking you know, up to K generations in the tree, and then I have to think about the edge weights sitting on top of this. Right. So now, you know, if you think about a vertex, so let's imagine conditioning on having gone out, you know, I levels in this process. So if we condition on gn ki and then look at a vertex, which is in the ith level, so in gn ki minus gn ki minus 1. Okay, so that's, let me draw it a little bit more schematically. So here's vertex 1, here's gn ki, and now here's a vertex u, which is on the top level. Okay, and now we're interested in understanding what gets added. What's the set SU that gets added in the next generation, right? And what are the weights of the edges on that set? So let's list those edge weights in increasing order. So on the edges from U to SU in increasing order as like WU1 up to WUK. Okay, so what are these? These are the k smallest values among a collection of edge weights, which are these NUE, right? Those are how we weighted the edges. And here E is UV, and V, we said, has to be a vertex sitting out there in the rest of the graph. So it's a vertex in N minus the vertices of GN KI. Okay, so this is, so it's the N smallest values among a set of size N minus, like, well, we don't know exactly how big this graph is, right? We add k neighbors at the first step, and then maybe as many as k squared at the second step, maybe less if there's some overlap, and so on. But certainly at each generation, we add at most at step I, we add at most k to the I edges, and we're thinking of k as bounded. Okay, so this whole process, when k is bounded, only removes an order 1 number of vertices from the game, from the complete graph. Okay, so we're basically looking at the n smallest values among n minus order 1 independent random variables like this. So then we're basically in the same situation we were when we just looked at the first generation. We're in a slightly smaller graph, but the difference doesn't make much of a difference. So that means that this vector WU1 up to WUK will converge in distribution to the first k points of a Poisson process, just like it did in the first generation. Okay, and so that's good news, because that's the asymptotic picture that we have in the Poisson weighted infinite tree. At each generation, the first k children look like the first k points of a Poisson process. And now all that we need to say that the asymptotic picture in the complete graph is the same as in the PWIT is to say that if we look at the neighborhood of SU and the neighborhood of another point S, U prime, that with high probability they don't overlap. Okay, but conditionally on what we've seen so far, the smallest weight edges, the symmetry of the graph means the smallest weight edges just go to uniformly random locations in what remains of the complete graph, right? So this is just like a uniform size k subset of what's left. This is another uniform size k subset of what's left, and k is of order 1. So with high probability, those two aren't going to touch one another. Okay, so since the sets SU, U in here, so are conditionally independent size k subsets of n minus the vertices of Gn Ki. So with high probability. They're pairwise disjoint. Okay, so that's almost the proof that that GNK converges to the Poisson-weighted infinite tree. Okay, what have we now shown? We've shown that here's the picture in GNK. We see, k neighbors that look like, whose weights look like a Poisson process, and then each of those vertices has k neighbors whose weights look like a Poisson process. Okay, and we have the same sort of picture over in PK. Okay, but there's one thing that we haven't looked at, which is over here. We have neglected to consider any potential other edges between these vertices, right? We didn't look at the weights between vertices in this tree, aside from the vertices that went from a vertex V to its new neighbors SV. So in theory, our local structure here could be messed up if there was some very low weight shortcut between two vertices in this picture. That would change the metric structure. So the last step is to sort of make sure that all of the other edges between these vertices in the complete graph have such high weight that they're not going to mess up the local structure. Okay, so finally, if I look at any vertices UV in this GNK, if neither of them was if you're not looking at a blue edge, so if U is not an SV and V is not an SU, then this edge weight UV is still, even conditionally, a uniform 0-1 random variable. And so that means that for any and these weights get multiplied by n, so they become huge after scaling. Okay, so for any real x, the probability that the minimum edge weight among the non-blue edges, so where U is not an SV and V is not an SU, of NUV, the probability any of those rescaled weights is less than x tends to 0. Okay, so that's saying all the edges joining these vertices have huge weight, huge length. Okay, now I think I finally understand the comment that Omer was making half an hour ago. Even if these edges have huge length, in principle, if I really care about the sort of precise graph theoretic structure, they do still, the structure here is different from the structure here. And I forgot to write that down in the definition of the sort of weighted local convergence. So we should really only look at edges whose length is less than whose length is less than a threshold as well. Okay, so we throw away excessively large weight edges, and I'm not going to go back and fix that on the fly, but I'll fix it in the notes. Okay. Okay, so that's an explanation, I think, which hopefully will be reasonably convincing of how the local structure of this rescaled weighted complete graph looks like that of the PWIT. Okay, and now there's a beautiful theorem of Aldous and Steele, which says that if you have local convergence of a sequence of graphs, then you actually also have local convergence of the spanning trees of those graphs. Okay, so So let me tell you that theorem, and then I think I have time to use it to explain what the sort of typical behavior of the weight of the minimum spanning tree is. And then in the next lecture, we'll focus on using it to understand more about the local structure of the MST. Okay, so this is a theorem from those two authors I mentioned earlier. So if we let, so Gn be a sequence of, so G star valued random variables. So I'll write Gn is Vn, En, rho n, and the weights are Wn. Okay, and I'm supposing that, so they're finite. So, I'm going to add in the limit right here, actually. So, Gn has n vertices. So, at least for the finite graphs, I guess then the infinite one will also satisfy that. And for the finite graphs, the root of Gn is uniformly random. Okay, so these are random. So saying, what does it mean to say the root is uniformly random? You can think of that as equivalently to saying, if you pick a random vertex and reroute at that vertex, then you don't change the distribution. If you pick a uniformly random vertex. Okay, so now let's suppose that almost surely no two edges. So there are no ties between edge weights in the limit. So no two edges of G infinity have the same weight. Okay. Then under those conditions, if Gn converges in distribution to G infinity in the space that we're considering, G star, D star, so in the local weak sense, then also, so if we look at the pair Gn with its minimum spanning tree, that converges in distribution to G infinity with its weighted minimum spanning forest, or wired minimum spanning forest in the product space, G star times G star. Okay, and moreover, not only does the minimum spanning tree converge to the wired minimum spanning forest, also the degree of the root converges to the degree, sorry, that should say MST. So the degree of the root in the minimum spanning tree of Gn converges to the degree of the root in the wired minimum spanning forest of G infinity, and that the expected degree in the minimum spanning forest is 2. And also there's convergence and expectation of the weights. So if I look at the sum overall edges of the minimum spanning tree of Gn, which contain the root, if I sum up all of those weights, then that converges in distribution to the sum, the corresponding sum for G infinity. And I don't have room to write it, but also expectation for that convergence. Okay, so so this is, I mean, this is quite nice, right? It says that as soon as you have convergence of the local, just of the weighted local structure, you also get convergence of this sort of combinatorial optimization type object sitting on top of it. The theorem is wrong as stated. It's also wrong in the paper that they wrote because you know, this object doesn't quite live in this space. The local structure. So, for example, you know, we'll see this shortly, but on the Poisson-weighted infinite tree, the minimum spanning forest will look something like this. You know, you'll have some edges that go off from the root, and that'll be part of the wired minimum spanning forest. But then there will be other parts of the wired minimum spanning forest which are sort of locally near the root that they're, you know, at a bounded weighted distance from the root, but they don't actually connect up to the root. This edge isn't here. Okay, so so you need to extend the notion of convergence a little bit to account for sort of binary information about edges, the presence or absence of edges within the wired minimum spanning forest. It's just a little addition that, you know, they didn't quite bother writing down. But if you want to make this sort of perfectly rigorous, then you should really have a slightly augmented notion of local weak convergence, which can account for that sort of binary information. And I didn't want to set up the G star in order to include that, because it would have taken us a bit far afield and taken a while. Okay, but basically the story is that, you know, if the graph converges locally with its weights, then the minimum spanning forest also converges locally with its weights. If there are no questions about the statement, I think now I'd like to try to show you what this theorem tells us about the weight of the minimum spanning tree. Okay, so let's try to study the limiting random variable. Okay, so let me write let's let W be this sum over edges in the wired minimum spanning forest. Now we're going to focus on the PWIT, because we know that the PWIT is the local limit of the complete graph, and that's sort of what I'm interested in. Okay, so I'll look at the wired minimum spanning forest, the PWIT, and then I'm going to sum the well, I only want the edges that contain the root. So, and I'll sum their edge weight, which remember in the PWIT is this Poisson edge weight. Okay, so then the expected value of W is 2 zeta of 3. Okay. So so I think I can prove this to you in 10 minutes. Let's draw the local structure again of the PWIT. We've got this root vertex. Its neighbors are weighted according to a Poisson point process on 0 infinity with rate function, which is just constant, right? And now, so what happens when an edge, so which edges are present in the wired minimum spanning forest? Remember that, so an edge UV is in the wired minimum spanning forest. So let's say of weight X is in the wired minimum spanning forest if and only if at least one component of the X percolated subgraph is finite. right? So that means that this means, you know, this phrase means only keep edges of weight less than or equal to x. Let's say less than x. Yeah. Right. So we saw this when we were studying free versus wired minimum spanning forests. The free forests, and we use this to show that the free and wired minimum spanning forests were the same when the graph had unique infinite clusters. Okay. So so let's think about what this means now for the you know, what are the odds that if an edge, you know, if an edge comes along in the PWIT and it has weight x, then what happens if we look at the x percolated subgraph? Well, you know, here's this vertex v. If you look at the subtree rooted at v consisting of only edges of weight at most x, well, the child edges are weighted by a Poisson process, right? So the number of children of weight at most x is just Poisson with mean x. And then each of those children likewise has a Poisson mean x number of children of weight at most x. Okay, so the subtree, you know, the component, let me call it tvx, you know, consisting of vertices joined to v by edges of weight less than x is distributed as a Poisson x bien-aimé tree, right? And so that means that, you know, the probability that I'm going to use this notation later, so I'm going to write x minus here to indicate that I want edges of weight strictly less than x and not less than or equal. Okay, so the probability that the component can, you know, in this x percolated graph, the component containing the empty set has the probability that both of these are infinite, that sort of this component over here is infinite and this component over here is also infinite. Well, those are independent Poisson x distributed bien-aimé processes. So that's just, you know, the survival probability for a Poisson bien-aimé tree, which we called theta, squared. So you need two of these trees to be infinite. Okay. So this edge makes it into the wired minimum spanning forest if this doesn't happen, if at least one of these is finite. So the probability an edge of weight x attached to the root makes it into the wired minimum spanning forest is 1 minus theta of x squared. Okay. So so this means that you know, the expected value of w is this total weight here, right? I can express, like in Jean-Christophe's lectures, you know, for this sort of function of a Poisson process, I can express as an integral against the rate function and then the probability that each edge gets added along with its weight. So we have an integral and the rate function is lambda x dx. Well, lambda is actually just 1 in our case, but I wanted to write it to emphasize it's an integral against the rate function. Okay, and then if an edge is added, we count its weight, x, and the probability it's added if its value is x is 1 minus theta of x squared. Okay, and so you know, the aim is the claim then, the claim and the aim is that the expected value that this integral has value 2 zeta 3. Okay, so that's 2 zeta 3. We want to show this. Okay, so since there's a question in the chat that I think deserves answering, and the integral isn't hard, but I don't want to squeeze it into 2 minutes, I think I'll I'll start next lecture by calculating this integral, and then we'll continue on to develop further properties of this local limit. There's this question, doesn't the PWIT have a tree-like structure? If so, wouldn't the minimum spanning forest be equal to the same PWIT? So this is a good thing to clear up. And it's related to the discussion at the start of Tuesday's lecture, which was sort of explaining the difference between the free and the wired minimum spanning tree in terms of boundary conditions. Okay, so remember the idea was if you take if you have an infinite graph, you can think of building a minimum spanning tree in sort of 2 ways. One is, so take a large ball of large radius r, and now take all of the vertices on the boundary of that ball. Okay, and you can do sort of one of 2 things. You can either just calculate a minimum spanning tree of this because I'm thinking of a locally finite graph, you can calculate a minimum spanning tree of this finite graph. So I'll call that MSTR, and now I've just left the boundary as it is. It's unchanged, so I'll call that free. And you can try to ask, does that converge to some limit? Okay, but another thing you could do is, take all of these vertices on the exterior and identify them into one big vertex representing everything that's far away. Okay, so wire them together, and if you do that, then now you've created new connections that sort of that pass through this big wired together vertex that pass through the boundary. Okay, so that all of those connections kind of in principle will break some other connections in this free minimum spanning tree and result in a sparser graph in here. Okay, so that's what you'd call the minimum spanning tree, the wired minimum spanning tree of radius r. Okay, and if you think about doing that on the Poisson-weighted infinite tree, right? If you go out some number of generations r here and you glue everything together at that level, then when you compute the minimum spanning tree, you don't necessarily have to see a sort of tree structure locally near the root, because some of the paths might go out to this big gluing out there and then come back like this. So you might see some paths going out from the root, but you might see other paths that sort of don't connect up to the root, and they're only a tree because of this big gluing at this far off distance r. Okay, so everything kind of connects up out there. So then the local structure that you see near the root really doesn't look like a tree if you only look at a bounded distance. You have to go out to this big gluing to see it. Okay, and in the limit, you don't see it at all. You sort of see this sub-forest of the tree, and you have to think of the trees of that forest as all kind of being glued together at infinity. That's the wired minimum spanning forest. Okay. So yeah, I mean, I sort of quickly glossed or mentioned, but very quickly at this point earlier in the lecture when I was saying it's important in this setting that we're looking at the wired minimum spanning forest, because the free one would just be trivial. It would be the whole tree. Good. Okay, so we'll finish computing this nice integral at the start of next lecture, and then we'll prove that the component containing the root in this wired minimum spanning forest is a one-ended object, almost surely, and talk a little bit about its volume growth. So thanks all for your attention. You quickly glossed over the sum over the edges. Somehow there's a change between summing over weights less than x in the integral. You mean when I went from, here I have a sum, and here I have an integral for the formula. Yeah. So the thing to think about is, I mean, imagine that I tell you, I mean, this is a sort of a general way of calculating expectations over points of a Poisson process. But the way to think about it is, if you imagine that I've told you that I haven't told you everything about this process. I've just told you that there is an edge of weight between x and x plus h attached to the root for some small h. And then I ask, what's the probability that that edge contributes to this sum? Then, that probability is approximately this 1 minus theta x squared. So, you can get at this sum, if you like, by doing some fine mesh discretization of the interval 0 infinity where the points are showing up, and then thinking about the expected contribution from each little slice to the overall sum here. Yeah, but it's some Poisson change of variable. I didn't know that zeta 3 was not known to be transcendental. Yeah, there's other zeta numbers that come up in these sorts of optimization problems. So if you look at the minimum weight matching rather than the minimum weight spanning tree, and you compute the expected weight, you get zeta 2 instead of zeta 3.
So that's in a bipartite graph, right? It as well.
I thought it was also on the complete graph. It's certainly on a bipartite graph, but maybe I'm wrong about the complete graph. Yeah, I can't swear to that anymore.
Yeah, I'm not sure either.